Yeah. Hi, everyone. So we're going to carry on with our work on matrices. So to start off with, we've got a few definitions to get through, and then we're going to go on to some functions of matrices. Okay, so the first definition is that of a square matrix. So definition. A square matrix is a matrix with the same number of rows and columns. Okay, so it has n rows and n columns. Yeah, so we've seen some square matrices before, so let's just do two examples here. So let's say 2 by 2, so same number of rows and columns. An example of that would be something like 1, 2, 3, 0. Yeah, that's a square matrix. It makes a square shape. Another example would be like a 3 by 3. This can be 1, minus 1, 0, 2, 3, 2, 4, 6, 7. Okay, again, it makes a square shape because the number of rows and number of columns are the same. Okay, so that is a square matrix. Okay, and then for the next definition, we have a special kind of square matrix called the identity matrix. So definition. The identity matrix is a square matrix with ones along the diagonal and zeros everywhere else. So that is an identity matrix. Okay, so what does it look like? Okay, the shape of the identity matrix depends on what size you're looking at. So if you're looking at a 2 by 2, okay, 2 by 2 square matrix, then we write the identity matrix as R2, okay, because it's a 2 by 2. And it's given by 1, 0, 0, 1. So here we see that we've got the ones along the diagonal, and then we've got the zeros everywhere else. Okay, so that's a 2 by 2 identity matrix. We can look at a 3 by 3 identity matrix, and we call that R3. So this is going to look like 1, 0, 0. 0, 1, 0, 0, 0, 1.
Someone gave this man a
so
trophy.
again, we've got the ones along the diagonal, and we've got the zeros everywhere else.
Look at me, stop doing whatever you do.
Yeah, and you can do the same for any n by n matrix.
Not wearing waist trainers, it's not wearing sauna suits.
It follows the same kind of pattern.
And it's definitely not giving up carbs.
Yeah, so what's the use of the identity matrix?
All you have to do is be in a calorie deficit for an extended period of time. Once your body
the identity matrix.
Nutrition and fat loss tips. This is how you get rid of your stubborn. You say lose weight, I say lose weight.
As a 1
I mean, if you are
during multiplication.
Say lose weight, I say lose weight relationship. I mean, if you want to fight, you can fight now.
Okay, so what do we mean by that? Well, with normal numbers, if you multiply by a 1, it doesn't change anything. So we have the same idea with matrices. If you multiply a square matrix by the identity matrix, it stays the same. Or if you multiply the identity matrix onto a column matrix, like single column, it stays the same as well. Okay, so we'll see a couple of examples. So let's say for a 2 by 2, if you have 1, 0, 0, 1, so the 2 by 2 identity multiplied by A, B, C, D, then you can quickly work this out. This is going to be A, B, C, D. Okay, so it stays the same even after multiplying by the identity. Now, the special thing about the identity is that you can multiply it on the left and on the right. So if we have A, B, C, D, we multiply it on the right, you can check, we also get A, B, C, D. Okay, so this is a special case of multiplication where the ordering doesn't matter. So for an n by n matrix, let's say M, we have that M times the identity is equal to the identity times M. Say that these are commuting. They're all commutative. Okay, so you can do the product in both directions, or if you swap them with the product, and it remains the same, we say that it's commutative. Okay, but this is a very special case. In general, we don't have this. Okay, so that was in yesterday's homework. So in general, we don't have this. Okay, so if you take two matrices A and B, then AB is not equal to BA. Okay, only under special circumstances will AB equal BA. Okay, and we can also look at the identity matrix multiplying other matrix shapes. So let's say we've got a 3 by 3, 1, 0, 0, 0, 1, 0, 0, 0, 1, multiplying A, B, C, like that. Let's check the size matching rule. So the first one is a 3 by 3. The second one is a 3 by 1. So we see that these match, the 3 and the 3, those match. And the resulting matrix will then be a 3 by 1. So we can check that. So if we do the dot product of the rows of the first one with the column of the second one, we see that we get A, B, C again. Okay, so that's another example of this identity matrix acting like a 1. So a little note here. Multiplying by the identity matrix doesn't change the column matrix. Okay. So you'll see this quite often in maths. Whenever you see the word identity, you should be thinking to yourself, doesn't change the input. So the identity matrix doesn't change the matrix when you multiply by it. If you have the identity function, it doesn't change the inputs when it outputs. So for example, the identity function that would just be something like f of x is equal to x. Okay, it doesn't change the inputs. So again, in maths, when you see identity, like that's over there, identity matrix, identity function, think to yourself, it doesn't change the inputs. It leaves it as is. Okay, so that's just a little extra thing to keep in mind. Okay, are there any questions so far? Okay, no questions. Okay, so that is the identity matrix. Okay, let's have a look at some functions of matrices. Okay, so the first function is called transpose, transposition. Transpose or transposition. Okay. So taking the transpose of a matrix is done by swapping the rows and the columns.
That is going to blow your mind. I guarantee no one has ever talked about this on TikTok. This is the same way that I used to make more than 10,000.
Okay, so given a matrix, if you want to find the transpose of the matrix, you swap the rows and the columns.
It's going to take you to
The transpose of a matrix A is given by A with we put a T as an exponent there. Okay, so that means we are taking the transpose or the transposition. Okay, so let's have a look at an example.
Let's conduct your ATO.
Okay, so let's say A is equal to 1, 2, 3, 4, 5, 6. So this is a 2 by 3 matrix. Okay, we want to find a transpose. So a transpose. We're going to swap the rows and the columns. Okay, so the rows are going to become columns and the columns are going to become rows. So 1, 2, 3, that's the first row. That becomes the first column. 4, 5, 6, that's the second row. That now becomes the second column. Okay, so we took this row 1, 2, 3. It then became the first column 1, 2, 3. The second row 4, 5, 6 becomes the second column 4, 5, 6. So now we see that this matrix is a 3 by 2 matrix. So you see that the columns, the rows and the columns swapped. So we had 2 rows before, now we've got 2 columns. We had 3 columns before, now we've got 3 rows. Okay, so those swap as well. So the 2 goes there and the 3 goes there. Okay, any questions on this transposition? Okay, let's have a look at some of the properties. Sorry, I got a question here. Okay, other people talking. Okay, yeah, please leave your mics on mute, okay, unless you have something to say. Okay. Okay, so let's have a look at some properties. Okay, so what properties are there of the transpose? So the first property is that A transpose, so if you do it twice, you get the original matrix back. So if you do the swapping and then you swap again, you get back to where you started. Okay, number 2. A plus B transpose is equal to A transpose plus B transpose. So you can think of this transpose as being distributed over the plus. Okay, so if you take the transposition of the sum, it's the same thing as the sum of the transpositions. Okay, the products is a bit trickier. If you have A times B transpose, then this is going to be B transpose A transpose. So you need to swap the order when you take the transposition of a product. Okay, so the A and B swap around, and then they each get the transpose. Okay, last property, number 4. If we have a scalar multiplied matrix, so CA transpose, then we can just take this constant out. So it will be CA transpose. Okay, so the C can come out of the transposition. Okay, there is another property with inverse matrices, but we're only going to go through that later in the week. Okay, so for now, we just need to know these properties. We will add on to them later on. Okay, any other questions on the transpose? Okay, let's look at the next function of matrices, and that is the trace. Trace. Okay, so the trace of a matrix is the sum of the diagonal entries of a square matrix. Okay, so that is the trace of a matrix, and we see that it only works for square matrices. If we go back to the transposition here, we see that it works for any size matrix, okay, because you're just swapping rows and columns. However, for the trace, it only works for a square matrix. Okay. The trace of a matrix A is given by TR of A. Okay, so the function name is TR, meaning trace. Okay, so let's look at an example. Okay, so let's say we've got A, and it needs to be a square matrix for this to work. So let's say 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we've got ourselves a 3 by 3 square matrix. We want to find the trace. So the trace of A is going to be the first diagonal element, which is a 1, plus the second diagonal element, that's a 5, plus the third diagonal element, that's a 9. Okay, so in this case, the trace is going to be 15. Okay, so whatever square matrix you have, you just sum up the diagonal elements, and that gives you the trace. Okay, so let's have a look at the properties. Okay, so the first property is that the trace of A plus B is equal to the trace of A plus the trace of B. So the trace of the sum is equal to the sum of the trace. Okay, property 2. The trace of C times A is equal to C times the trace of A. So here we see this constant. We can take it outside of the function. Okay, number 3. This property relates the trace to the transposition. So the trace of A transpose is equal to the trace of A. Okay, so it doesn't matter if you take the transpose or not, the trace remains the same. So before and after transpose, it remains the same. Okay, then number 4, the trace of A times B is equal to the trace of B times A. Okay, so if A and B are both square matrices, okay, which means you can do left multiplication and right multiplication. So it doesn't matter what the order is, the trace remains the same. Okay, so A and B, you can swap them. Okay, this can be extended to more than 2 matrices being multiplied, and this gives you the cyclic property of the trace. Okay, so I'll show you what I mean now. So if we have the trace of A, B, C, D, and this can continue, this is equal to, and now we call this a cyclic property. So what we mean is a counterclockwise rotation of the elements. So you take A, which was in the front, and you move it to the back like that. Okay, so your counterclockwise rotation. So this is equal to the trace of B, C, D, and now we have A at the back. Okay, and we can do this again. B is in the front. We can put it to the back. This is equal to the trace of C, D, A, B. And we can do it again. We can take the C. We can move it to the back. This gives us the trace of D, A, B, C. And we can do this one more. D, we can put it to the back. We end up back where we started, the trace of A, B, C, D. Okay, so it has to be in this fashion here. You can't swap any elements. So A and C, you can't swap them around. It has to be this cyclic permutation of the elements. Okay, so this is called the cyclic property of the trace. Yeah, because we can cycle through the elements. Okay, and it has to be this counterclockwise thing. So you take the first element, you put it at the end, and then you can repeat that as many times as you want. Okay, and the trace remains the same. Okay, and we can see that property number 4 is just a special case of this, because if we take element A and we move it to the back, then we just get BA. Okay, so cycling through 2 elements is the same as swapping them. So 4 and 5 are pretty much the same property, but 4 is just a special case. Okay, any questions on the trace? Okay, let's have a look at the next function of matrices, and that is the determinant. Okay, so the determinant of a matrix let's say A is given by, okay, and there's two notations that we can use. We can either say det of A, so det, that's short for determinant, or you can use like the absolute value signs, but now with a matrix. Okay, so the absolute value signs with the matrix inside, that's another notation for the determinant. Okay, so how do we find the determinant? Well, we do it in stages. We define the determinant for a 2x2 matrix, and then we extend this idea for an n by n matrix. Okay, so let's start off with the 2x2 matrix. So I'm going to use the absolute value notation. So if we have A, B, C, D, okay, we want to find the determinant. This is given by AD minus BC. Okay, so we get a number in the end. Okay, so the determinant of a matrix is just a number. Okay, now we are going to extend this step by step to an n by n matrix. So let's look at a 3x3. Okay, so now we're looking at the determinants of A, B, C, D, E, F, G, H, R. Okay. Okay, so again, has to be some square matrix. So here, 3x3. This is equal to A, which is this first entry here. Okay, so we put down an A. And then what we do is we block off that row and that column. So the row containing A, we cross it out. The column containing A, we cross it out. And we look at the 2x2 matrix that's left over. So that is this E, F, H, R. And we multiply A by the determinant of E, F, H, R. Okay, so that gives us our first part of the determinant. Next, we put a minus B, so that is the second bit. Okay, so now let's look at what we do for that. So that's B. And then we do the same sort of thing. We cross out the row containing B. We cross out the column containing B, and we look at the remaining matrix. So that is this, D, F, G, R. And we take the determinant of that. Okay. Then it's going to be plus C. So you see how the signs alternate. It's plus A minus B plus C. And then I think you can see what we're going to do next. So that's B, D. We've got the C term. We cross out that row containing C. We cross out the column containing C, and we look at the resulting matrix that's left over. That's D, E, G, H. And we take the determinant of that. Okay, we add all of this up, and that gives you the determinant of a 3x3 matrix. Okay, are there any questions about that? Okay, and then this can be extended to a 4x4 matrix. Let's say we have A, B, C, D, E, F, G, H, R, J, K, L, M, N, O, P. Okay, so we've got a 4x4 matrix. We do exactly the same thing. So this is going to be A. So we've got A here. We cross out the row containing A, the column containing A, and we look at the leftover matrix. So it's going to be A times the determinant of F, G, H, J, K, L, N, O, P. Then we have minus B and so on. So minus B times that little determinant that's left over. Then it's going to be plus C times the determinant of the leftover. Okay, and then minus D times the determinant of the leftover. So plus dot, dot, dot for the resulting terms along that row. So you have the A term, the B term, the C term, and then the D term. Okay, and then this can be extended to any n by n matrix. Okay. Let's have a look at some of the properties of the determinant, and then we'll have a look at the homework question. Okay, so properties. Okay, so number one, if you have the determinant of C times A, where A is an n by n matrix, then this is given by C to the n determinant of A. Okay, number two, if you have the determinant of A transpose, this is the same thing as the determinant of A. Okay, so transposition doesn't affect the determinant. Okay, and number three, if we have the determinant of A times B, with the product of matrices, then this is going to be the determinant of A times the determinant of B. Okay, like that. Okay, and then you can extend this to other products as well. So if you have the determinants of A times B times C, then you can figure out what that needs to be as well. Okay, so number four, or let's say 3 star. Determinant of A times B times C, what would that be? Okay, so leave that for the first bit of homework. And then the main homework question for today. Okay, just before we get to the homework, are there any questions about the properties? Okay, let's have a look at the homework then. So prove that the determinant of an upper triangular matrix and a lower triangular matrix is the product of the diagonal entries. Okay, so what is an upper triangular matrix? Well, that is a square matrix where you only have entries in the upper right part of the matrix. So it looks something like this. A, B, C, then we have D, E, F, something like that. And then we have zeros everywhere else. Okay, so this is an upper triangular matrix. Okay, we see that the entries form a triangle in the upper right corner. Okay, so you've got a little triangle there. So that's why it's called a triangular matrix. Okay, that's an upper triangular and then a lower triangular. You can imagine what that looks like. That's going to be A, B, C, D, E, F with zeros everywhere else. And again, you can just draw in the triangle here. So we see that the entries form another triangle, but now in the lower left corner. Okay, so the first one we call upper triangular. And the second one we call lower triangular. Okay, so the homework is to prove that given an upper triangular matrix or a lower triangular matrix, if you want to find the determinant, then you just need to find the product of the diagonal entries. Okay, so that's this diagonal over here or this diagonal over here. Okay, so that's your homework for today. Okay, are there any questions about what we've done today? Okay, are there any questions about what's coming up in the summative quiz for today? Is there anything that you would like to go through? Okay, no questions on that. Okay, so we won't be having the second lecture today. Okay, so it's supposed to be a double, but we'll just leave that for today. Then we will carry on Thursday and Friday with the inverse of a matrix. Okay, so remember we did the matrix multiplication. Now we're going to look at matrix division using inverses of matrices. Okay, if you do have any questions later on, just email me or you can post your questions to the WhatsApp group. Okay, but then I will see you in the tutorial later today. Okay, bye everyone.